Starting with part 2 of chapter 3, what we saw in part 1 last time, we saw that if I have a vector A, I can split it to its x component and y component. One is along x direction, the other one is along y direction. And I can just move this along y direction vector and bring it right here, kind of looking like a triangle shape. So one side of a triangle is the portion of vector along x direction. One side of it is the portion of vector along y direction, and the vector itself is right there. So kind of like a triangle thing. Now, you might have seen this before. So if you have a triangle and we have a hypotenuse here, right there, which we just showed with h, so side across from the right angle. So this is the right angle of 90, right? And whichever side that is right in front of it. So this side is hypotenuse, right? Now, we have, so this is angle theta, for example, and then the side that is in the opposite direction. So length of a side opposite to angle theta, meaning that this is HO, standing for opposite, and this side, okay, is the length of the side adjacent to the angle theta. So remember, the most important thing is to identify the hypotenuse here, right there, the side that is in front of, across in front of the angle 90, the right angle. And then you have one which is opposite, HO, and one that is just like very close, adjacent to the angle. All right, so identify this. Why is it important, by the way? The reason it's important is, take a look at this. You have a triangle here. If you have a vector A and you split these vectors to its components along x and y, you're ending up with a triangle thing. Triangle that you have it right here. Okay, now if you want to write sine, cosine, and tan of this theta, so sine of theta is the side that is in the opposite, which is HO, divided by hypotenuse, H. Cosine of theta is the side that is adjacent to the angle theta, which is HA, over the hypotenuse, which is just H. Okay, and tan of theta, okay, is just HO, the side that's opposite, over HA, adjacent to angle theta. All right, so remember these three things. These are very important. If you, if you can write this and put it in the side of your computer, or to the door of the fridge to take a look at it every day, that would be great. I have them right here as well. So sine is opposite over hypotenuse. So sine is HO over H. Cosine is adjacent over hypotenuse, so HA over H. And tangent is the opposite over adjacent. So tan is HO over HA. Or we all know that tan is just sine over cosine, right? So if you don't, this is also very important. Tan of an angle is sine of that angle over cosine of that angle. Okay, you have to be a little bit careful because, okay, so tan is y over x, and just the same stuff that we have here, right? But you have to be careful because these are also known as polar coordinates, okay? So this depends on the orientation of the right triangle, and it's not always true, but if these definitions will always work if you measure your angle counterclockwise from the positive x-axis. So in other words, kind of like what we had. So we had x and we had y, and this is a vector, for example, vector a along y direction, a sub y, and a along x direction, a sub x. So in this angle, if you measure your angle counterclockwise from positive x, so counterclockwise from positive x, for example, 30 degrees. Okay, kind of like the car that we had here. You remember this? Let's see, this one. If I measure it from here, meaning that this is 0, this is 90, this is 180, this is 270, and going back to 0, it is 360. So 0, 90, 180, 270, 360, 360 degrees total angle, right? So if I measure it from this point, from this line, this type of formulas that we just talked about will always hold, will always be true. Let's take a look at that. Okay, as I said, it is important to identify the hypotenuse. So it is important to identify where the right angle is. It's right there, okay? So that is the right angle. And this is angle theta. So this is theta. So that means this is h. This is h of opposite direction. And this is h of adjacent, which I'm just showing it as h sub a, okay? Now, if that's the case, I have sine of theta being h sub o for opposite over h. I have cosine of theta being h sub a over h. And I have tan of theta being h of o over h of a. Okay, let's take a look at another example here. As I said, it is important to identify the right angle, then identify the hypotenuse. So the right angle is right there, 90 degrees, correct? 90 degrees. So this is h. And if this angle is theta, okay, this will be HO and this will be HA. So this side is HO, this side is HA. All right, so sine again of theta is opposite over hypotenuse. Cosine of theta is HA adjacent over hypotenuse, which is just h, and tan of theta is HO over HA. Okay, now a lot of times we're not asking you to find a sine or cosine or tan, especially in vector analysis. We're not asking you to find a sine of a angle because we're not directly dealing with math here. We want to use the math and mathematics to find what we are looking for, to find the direction. We're looking for directions a lot of times in vector analysis. So I can use sine, cosine, and tan, okay? So these three to find theta, and that's what I'm caring for because we're dealing with direction here. So I want to know with what direction, with what angle. For example, a ball was, moved, or a car started to move. So if I want to find the theta, I can use cosine, sine, and tan to use theta, and that's what I'm ultimately looking for. If you want to do that, then that's the formulas that you're going to use. So, for example, remember in this case, identify the right angle, which is right here. Okay, that's where the angle is. And and this is theta. This will be HO, this will be HA, and that will be our hypotenuse. So just H. So sine of theta is HO over H. And if I want to find theta, right there, this guy, okay, theta is sine -1 HO over H. All right, so that is the way that you can find theta that you're looking for. A lot of times we're asking for that, in fact. We will give you the information of HO, we'll give you the information of HA, just like what you had here. So just put this triangle in your mind for a second. This is exactly looking like this, isn't it? You have HO right there. You have HA right there. You have the values for them. And we're asking you to find theta, this angle. All right? So that's the way to do it. So cosine of theta is H sub A over H, meaning that theta is cosine -1 HA over H, right? So in order to find theta, you have different ways to do it, depending on what you have as your initial information, as the information that is being given by the problem, or it's been given by the question. And then based on that, you can, do this type of analysis to find theta. Okay, now, I'm pretty sure that almost all of you have seen this before. Okay. Pythagorean theorem, you've seen it before. I'm pretty sure if you haven't seen it, at least you've heard about it. So what it says is that if you have the opposite side, so let's say that this is our theta right there. The opposite side is HO. If you have this to the power of 2 right there, and you have the adjacent side, and you make that to the power of 2 as well. Okay, so you kind of multiply it by itself. So HA times HA, or HA to the power of 2. All right, and if you add them up, you'll get the hypotenuse to the power of 2. Okay, in other words, H is equal to under the square root HO squared plus HA squared. So Pythagorean theorem is exactly what I just wrote here. You can find the hypotenuse based on the length of the opposite side and the length of the adjacent side. Using this theory, you can find the H, or the value that the vector had. Only if this theory is is holding only if the angle is 90. Okay, you cannot apply this theory to something that is not angle of 90. So you cannot apply it to something like this, a triangle like that with angles of 60 degrees. You can't do that. You just cannot apply this theory to any triangle, right? It has to be a right angle triangle, a right angle of 90 degrees, all right? So let's take a look at this little example. So given that A plus B equals C, and that the magnitude of A plus magnitude of B equals magnitude of C, how are vectors A and B oriented with respect to one another? Okay, so they are perpendicular to each other, they are parallel and in the same direction. They are parallel but in the opposite direction. They can be at any angle to one another. I think the answer is obvious. They are perpendicular to one another, meaning that they are making an angle of 90 degrees. So, for example, if this is A, then this is B. Okay. So, it's often easier to work with scalar components rather than vector components. And that's where those unit vectors comes. Those unit vectors are, as I said, are crucial and important, are playing an important role in our, vector analysis. So it's important to kind of be able to work with them. Okay, A sub x and A sub y are the scalar component of vector A. X hat and y hat are unit vectors of magnitude 1. So if I want to write down vector A, I can write it like this. Okay, I can say vector A has a projection along x, which is just A sub x times the unit vector along x plus projection of A along y times the y hat or unit vector along y hat, or I can just write it like that. A is A sub x, the portion of it along x, I hat, plus the portion of it along y, j hat, okay? So that way I am presenting a vector to you, okay, based on its projection along x and y. It is still in the vector formation. It is still in the vector notation, okay? Meaning that I am keeping the notation being accurate. Both sides are vector. Left-hand side is vector. Right-hand side is also vector. A number times unit vector along x, a number times unit vector along y, okay? Now, so it's important to be able to work with these components along x direction, what the component is along x direction, what the component is along y direction. We'll get to these in a little bit as well. And try to also work backwards. A lot of times, you have the vector, you have to find the x component or along the x, or the projection along the x. Or you have that, if you have that, you can find the actual vector. So either way you can work backwards. And a lot of times we know the results, and something that we can do is to write two vectors, one along the x direction and one along the y direction, and we can just add them up along x or y directions. So example number 1. A displacement vector has a magnitude of 175 meters and points at an angle of 50 degrees relative to x direction. See, displacement, okay, is a vector. I need a magnitude, which is 175, and a direction. Everything is given. You know what the magnitude of the vector is, you know what the direction it is at, okay? Now I have given you enough information. The question is asking, find the x and y component of the vector. Okay, so I have x direction right there, I have y direction right there, I have my vector, 175, so I know r, we're just showing it with r, doesn't matter, you can show it with anything. So it is 175 meters, okay? And this 175, or r, this r, has a component along x direction and has a component along y direction. As I said, I can just move this component along y and bring it without changing its direction, without changing its magnitude. I can just move this guy and bring it all the way to this point. So it looks like a triangle now. Okay, one more time. This is x, this is y. I had vector A, this vector A had a sub x and a sub y, a along x direction, a along y direction. I can just get this y projection and I can, without changing its magnitude, without changing its direction, moving it to this point, okay? Making the triangle. All right. Now, it's asking to find those components. Okay, it's actually very easy. And by the way, here we are showing the component along x just by x and the component along y just by y. We could have shown it with like r sub x and r sub y, r along x or r along y, or we can just show it with, you know, x and y. It doesn't really change the physics of the problem. Okay, now identify the 90 degrees angle. That's the 90 degrees right there. Okay, so as soon as you identify this, and this angle is also given, it says 50 degrees with respect to relative to the x-axis. So you have this as your theta. So this is your theta. Okay, so right now you can just write, so this is your theta. You can just write the sine of theta being y, okay, over r, correct? H of O, let me actually write it like that. It will be more efficient. Sine of theta is h of opposite over h, so which is y over r. So sine of 50 degrees is y over r, which is 175. Now y therefore is 175 times sine of 50. Put this in the calculator. You can find the x, right? Just by using cosine. Cosine of theta is h sub a over h. H sub a is just x right there. And h is 175, right? So x therefore is 175 times cosine of 50. So cosine of 50 times 175 is my x, or the projection of vector along x direction. So I found the y, or I found the r along y direction, and I found the r along x direction, right? Yeah. Okay. Okay, so if you do that, then we found the x component being 112 meters. So after solving it for x, after putting this in the calculator, the final answer is 112 meters along x direction, and along y direction it's 134 meters. So we can write at this point, we have the portion along the x, the portion along the y. Then we can write the formula like that, like this equation. 112 x hat 130 plus 134 y hat. Or you could just write it like this. You could just write r equals 112 I hat plus 134 j hat. Okay. You're presenting your r, your vector r, with two components, one along x direction and one along y direction. One within 112 magnitude along x and 134 along y. So 112 times I hat, or 112 I hat plus 134 j hat will be your vector r. Okay, so this is known as vector notation. I am using a different type of notations to write what I want to say, right? So both sides are vector. Both sides are vector. Very important. Left-hand side is a vector. Right-hand side is also a vector. All right. So, but the notations are vector notations. I'm using I and j to indicate that I have this much of vector is along x, this much of it, and this vector is along y. Okay. So this is called the vector notation. It's important to play with them, to use this notation until you get used to it. You have not seen this notation before, maybe even if you've taken maybe a lot of mathematics classes before, you might not have seen this notation before. Okay, this is a vector notation. It's actually very useful and very, very useful. Okay, let's take a look at this this example. If a component of a vector is double, if each component of a vector is double, how many components does it have? Two components, one along x, one along y, right? If each component of a vector is double, what happened to the angle of that vector? Okay, so it will double, it increased, but by less than double, it does not change, and it is reduced by half. So let's take a look real time. We don't want to guess. I mean, some of you might know the answer, but let's play with this. So I have so let's do this. I have my x direction and my y direction. Okay, so that's x and y. And then I have my vector right there. Okay, with an angle of whatever, with an angle of let's say theta. So if this is vector A, this would be the portion of it along x direction. So A sub x, and this would be the portion of it along y, A sub y. And they are all vectors, by the way, so we have a vector quantity both for x and y, right? Now, it says if each component double, what would happen to the angle? So let's write down the sign of that. Sine is identify the 90 degree, which is right there. Okay, this is the 90 degree angle right there. So remember the formula, H, or let's actually write down, why not? Let's actually write down the tan of it, the tangent. That's much more useful. So the tan of theta is HO, opposite of HA over HA. So tan is the component along y direction and a component along x direction. Okay, so that's the tan of theta. All right. And they are vectors, by the way, they are vector quantities. So if you divide the vector, the magnitude of that vector along y over divided by along x direction, you will get the tan of theta, right? So this is something that we have seen before. Now, if that's the case, if I double each side, if I double each component, the tan of theta, if I double it in both directions, both x and y, what happens is that this factor of 2 will cancel from top and bottom. So this 2 will cancel out this 2. Now I am left with the same ratio as before. So the tan of theta does not change. So that means the angle doesn't change. Meaning that if you double this side, if you double this side, this, you have changed the vector for sure because you have changed its components, but you haven't changed the direction because you have changed the components with the same factor, with the same magnitude. Okay, this is the end of part 2. We'll go to part 3 after this.